Welcome back to our series on multivariable calculus. In this episode, we're going to talk about other coordinate systems. That is, systems that are different from the traditional rectangular Cartesian coordinate system, namely polar, cylindrical, and spherical. The polar coordinate system is probably the one that you have the most familiarity with because it is generally covered in a good course in advanced algebra. In the polar coordinate system, the x and y axis are instead replaced by an r theta axis. That is, every point in the plane is described by a radius and an angle. The radius, of course, is the absolute distance from the origin to the point. So this represents the radius. The angle then is measured from the positive x-axis in a counterclockwise direction until we reach the radius. This is theta. What's important is that the polar coordinate system can easily identify points in the two-dimensional plane just as easily as x, y. It just does so with different coordinates. It describes all points as lying on a concentric circle around the origin of radius r, and it describes that particular point on the circle as being deflected from the x-axis by a particular angle. You can see that this just as easily describes points in the two-dimensional plane as the x, y coordinates do. What's important for us, though, is to derive conversion factors between the x and y coordinates and the r and theta. The only way that these alternate coordinate systems will be useful to us is if we can move seamlessly between rectangular coordinates and these alternate coordinate systems. Okay, in this case, that's pretty easy. It's just some right triangle trigonometry. If I drop a vertical line down from the point, this represents its y coordinate, and the distance over to that perpendicular represents its x coordinate. And some simple right triangle trigonometry will tell me that the x coordinate is actually located at r cosine of theta, and that the y coordinate is located at r sine of theta. This way, I could take any r theta designation of a point in a plane and convert it easily into its xy analog. To undo that change, rather to take an xy coordinate and find its r theta, we'd apply the following principles. Because r is just the radius and it's the hypotenuse of this right triangle, then r uses the distance formula with the x and y coordinate, x squared plus y squared under the radical. So that's how we could find r from x, y. And then finally, because x and y represent the vertical opposite side of the angle and x is the adjacent side, the inverse tangent ratio of the angle will provide the y over x coordinate. So theta will be equal to the arctan of y over x. I'll add an asterisk to this one because you have to be careful in its application. Any points in the first or third quadrant are always treated as if they're in the first quadrant. And the reason why is that the inverse tangent ratio can't distinguish between a plus and over a plus and a minus over a minus. Correspondingly, angles in the second and fourth quadrant are mistaken for each other. In essence, all this inverse tangent can do is place a point either in the first quadrant or the fourth quadrant. You'll have to notice when the point is actually in the second quadrant or the third quadrant so you can correctly assign the angle by adding 180 degrees. Other than that, these formulas work pretty flawlessly at shifting points and even functions into and out of polar coordinates. The second coordinate system we're going to look at is the cylindrical coordinate system, and it's strongly related to the polar coordinate system, so much so that the formulas will really work quite easily, translating from one to the other. This is a three-dimensional coordinate system. That is, it has x, y, and z components, and in cylindrical coordinates, those are r, theta, and z components, or coordinates. R, of course, is the radius, but it's not the radius directly to the point. Instead, we drop a perpendicular line along the z-axis to the point that would lie in the xy plane immediately under this point. And if I draw a radius out to that, that's the r that we're talking about. Notice it's the same radius that we use in polar coordinates. It's just the radius to the projection of the point in the xy plane instead of being the radius directly to the point. Theta is also replicated. Theta is the angle from the positive x-axis to that radius in a counterclockwise direction. The third coordinate, of course, is the z-coordinate, and that's right here, and that goes unchanged. The z-coordinate in cylindrical coordinates is the same as the z-coordinate in rectangular coordinates. You'll notice that now every point that lies in cylindrical coordinates lies on the surface of a cylinder basically that's given by a vertical side of z and a circular base of r and theta. That's why it's called cylindrical coordinates. It kind of defines a cylinder in 3D space. Okay, well, let's look at the conversions between Cartesian coordinates in the Cartesian axis and cylindrical coordinates in the r, theta, z. Well, as you can see, we can simply carry these right over. X and y are defined in the xy plane, and they're defined by r theta in the same way. So x will equal r cosine of theta, and y will equal r sine of theta in cylindrical coordinates. R will be the square root of x squared plus y squared, and theta will be the inverse tangent or arctangent of y over x. With the same caveat it had before, we have to be careful in the xy plane between the quadrants we're in, because we could have a 3D coordinate in the third or second quadrant of the xy plane in 3D space, and we'd run into the same issues where the inverse tangent would misassign the angle. So be cautious about where the point lies before you find the theta angle from the x and y coordinates. Finally, the z coordinate goes unchanged, so this formula works both ways. Z in cylindrical coordinates is the same as z in rectangular coordinates. So the z value is simply retained. So there are the conversion formulas into and out of cylindrical coordinates from 3D space. Now let's talk about spherical coordinates. Spherical coordinates define a point in terms of the three coordinates rho, theta, and phi. Rho is the radius to the point from the 3D axis. If we project that radius down into the xy plane, then theta is the angle that that projection makes with the positive x-axis in the counterclockwise direction. And finally, phi is sort of the tip angle. It's how far rho is deflected from true vertical measured from the z-axis. So rho, theta, and phi define points in 3D such that all points lie on the surface of a sphere of radius rho, and hence the name spherical coordinates. Well, let's take a look at how rho, theta, and phi relate to the x, y, z axis. So just as we could for cylindrical and polar coordinates, we can convert things in and out of spherical coordinates. Well, the first thing we can borrow is that the spherical coordinates for theta are very similar to what they are for cylindrical, with one caveat. This line right here is not the true radius. The radius is rho. This is just the projection of that radius into the xy plane. So first, let's solve for what that projection is. Because this represents true vertical, as does the z-axis, that phi angle could just as easily be written here. Because this is a right angle, being the angle between vertical and the projection of rho into the xy axis, this right triangle features rho as its hypotenuse and phi as its vertical angle at the top. Well, that means the length of this side is given by right triangle trigonometry. This will be rho times the sine of phi. And that represents the radius in polar coordinates so that we can now find what the x and y coordinates are. The y coordinate would be out here and would trace over parallel to the x-axis. And of course, the x coordinate would be here and would trace over parallel to the y-axis. Let's solve for what those coordinates would be. First, for x, because x is still equal to r cosine theta, it being measured from the positive x-axis. It's just now the radius is this rho sine phi, so it would be rho sine phi times the cosine of theta. And the y-coordinate correspondingly would be r sine theta, but r is provided by rho sine phi. So this would be rho sine phi sine theta. And those are the x and y coordinates in terms of rho, phi, and theta. For the z coordinate, it's a little bit easier. After all, z represents sort of the height of this triangle right here. This is its z coordinate. And of course, it's adjacent to phi in a right triangle whose hypotenuse is rho. So the cosine theta should provide for what z is. Z will actually be equal to rho cosine of phi. So there's x, y, and z. Let's go ahead and undo these so that we can then figure out what rho and phi and theta are in terms of x, y, and z. First, rho. Rho's the easy one. Rho is simply the distance formula from the origin to the point rho phi theta. So its x, y, and z coordinates fit into the hyperpythagorean theorem. It'll be the square root of x squared plus y squared plus z squared. Next, to calculate what theta and phi is in terms of x, y, and z. The first one's the easiest one to find, and that's this one right here. I can find the phi coordinate just by solving this for phi. And of course, that would be z over rho, and then the arc cosine of that. And that is the phi coordinate on its own. Of course, rho is the hyperpythagorean theorem. So if we substitute this in here, there's phi in terms of inverse cosine of all x, y, and z coordinates. And then the final one is to solve for x and y, or for theta. And the easiest way to do that is to simply take the ratio of these. Notice rho is in both and sine phi is in both. So if I divide the y coordinate by the x coordinate, I once again get the inverse tangent of y over x equals theta. So theta is still equal to the inverse tan of the y coordinate over the x coordinate. And this will share the same caveat that it had before. As I move points around in 3D space, if they end up in the xy plane in the second or the third quadrant, then you'll have to be mindful of these x and y coordinates in order to make sure that theta is correctly assigned. So there it is in spherical coordinates, cylindrical coordinates, and polar coordinates. You now have the ability to move individual points and functions between these different coordinate systems. You may very well ask the question, what is the value of these different coordinate systems? If they're just different ways of representing the same thing, what value do they have? And the answer is symmetry. There will be a number of functions that are simply much, much easier to represent in these various coordinate systems. So it's more out of convenience than necessity. None of these coordinate systems are imperative, but they do make our job easier. And of course, much of mathematics is about finding useful shortcuts and simple representations. So think about that as you contemplate these coordinate systems.